do a couple of problems on chapter 11 before we define convexity and other things. Okay, so the first question we are going to do is trying to show that suppose f is increasing, suppose f prime is increasing, then show that every tangent line intersects the graph of f only once. Then show that every tangent line intersects the graph of f exactly once. Okay, proof. Now there's a hidden implicit assumption that is being made that in this statement, when we say f prime is increasing, it actually implicitly tells us that f prime is defined for every point f. F is differentiable at x for every x. Okay, so we know that the derivative of f exists at every point x. Now suppose we are going to assume the contrary. We are going to assume that there is a tangent line which cuts the graph twice. Suppose the tangent line at x is equal to a cuts the graph again, at x is equal to b. Okay, therefore the slope of the tangent line is equal to slope of the secant line from a to b. F prime of a is equal to f of b minus f of a over b minus a, right? Where this is the slope of tangent line at a, slope of tangent line at a, and this is the slope of the secant line from a to b, right? Now I don't know if f prime is continuous or not, f prime differentiable or not. I don't know any of the properties of f prime. What I do know is f prime exists everywhere, and because f prime exists everywhere, f prime exists at x for every x implies f is continuous at x for every x, right? Because f prime exists at every x, f is continuous at every x. And if my x is continuous for every x, then f is continuous from a to b. Therefore, f is continuous on a to b and differentiable on a to b, and therefore by mean value theorem, there exists let's say y belonging to a b such that f prime of y is equal to f of b minus f of a over b minus a. Well, but f of b minus f of a over b minus a is exactly equal to f prime of a, right? Which contradicts that f prime was increasing. So I am getting, therefore, y is greater than a, and f prime of y is equal to f prime of a, contradicting f prime is increasing, right? And therefore such a b cannot exist. Therefore such a b cannot exist, cannot exist, and therefore every tangent line cuts the graph exactly once. Every tangent line intersects the graph exactly once. Okay, the same exact result is true even if your function f prime was decreasing, right? Because then you'd get the other way around, that, oh, y is greater than a, but it shouldn't, their values are equal, f of y is equal to f of a, which cannot happen, right? So that's question 1. Question 2. Prove that if a function is bounded, prove that if f from some interval I to r has a bounded derivative, then f is uniformly continuous on I. Is the converse true? Is the converse true? Okay. Proof. So I'm going to leave the is the converse true part for you guys to work out. It's not too hard. Okay. Here's how the proof goes. You should be able to figure out, try to figure out how you would possibly make the proof fail, right? So what does it mean by f from I to r has a bounded derivative? It means that for every x in I, it means that there exists m greater than 0 such that for every x in I, f prime of x is, well, smaller than m, right? It is bounded. When we say bounded, we mean upper bound as well as lower bound. So absolute value of f prime of x is smaller than m, right? So we want to know if I can find that f is uniformly continuous on I. Can I show uniform continuity? So let us take some points x and y. Okay, suppose x comma y belong to I, right? Then what do I want? Then x minus y smaller than delta, given any delta, implies, well, I want to find something about f of x minus f of y, right? What do I know? Well, maybe I shouldn't have gone with implies, but what do I know? Okay, let me do this slightly differently. Suppose x comma y is in I, then f of x minus f of y over x minus y, well, by mean value theorem, there exists z in I such that this is equal to f prime of z, right? Technically, z belongs to x with x smaller than z smaller than y, right? Because we have bounded derivative, the derivative exists everywhere, and such a thing exists by mean value theorem, right? Which means, therefore, absolute value of f of x minus f of y over x minus y is equal to absolute value of f prime of z, which is smaller than m. And therefore, f of x minus f of y is strictly smaller than m times x minus y for every x comma y, right? Therefore, if x minus y is smaller than delta, x minus y is smaller than delta implies f of x minus f of y is smaller than m times delta, right? And so how do I show uniform continuity? Therefore, given epsilon greater than 0, take delta is equal to epsilon over m, then x minus y smaller than delta implies f of x minus f of y smaller than delta times m, which is equal to epsilon as required. And since this delta is independent of y and x, this means that the function is uniformly continuous. Therefore, as delta is independent of x comma y, f is uniformly continuous on I. Okay, so in the next video, I will show convexity and related results.